Okay, so we are going to start looking at more advanced projection techniques where we're projecting on a bigger subspace than a one-dimensional subspace. And actually, what's going to happen for us is that these subspaces are going to grow with each iteration. So it's going to be a different type of iterative method than we saw before. So I'm going to give sort of an overview of the iterative method. I'm going to give I'm going to give you a method that we're not going to use. So in other words, I'm going to give you a description of a method, and then I'm going to say, here's one way that we could implement this method, sort of the most obvious or naive way of implementing this method. And then I'm going to say, well, here's why this method doesn't work. And then in the next video, I'm going to tell you the method that we're actually going to implement. Now, the overall method I'm describing itself is not a great method. There are updates to this method that make it much better. So it's similar to how, the SOR method is great, but if you don't understand Gauss-Seidel, SOR is hard to understand, and if you don't understand Jacobi, Gauss-Seidel is hard to understand. So we learn Jacobi so that we can understand SOR. That's kind of what we're going to do here. We're going to learn several different things, but the setup is going to be the setup I'm going to give is going to be very similar to stuff that we're going to be doing for basically the rest of the semester. All right, so here is the setup. We're going to have some problem that we want to solve. AX is equal to B, and we're going to form an initial guess. So usually the initial guess will be equal to 0. So we're going to form A times X naught, and we're going to subtract off B, and this is going to be the residual. Of course, that's the negative of the residual, so let me write it the way that we normally write it, which is R is equal to B minus AX0. Okay, and just to let us know what we're dealing with, we're going to call this R naught is equal to B minus AX0. Okay. So what we're going to do is we're going to build a set of subspaces, and at each subspace, we are going to go from X naught to a vector in that we're going to go from X naught to X naught plus a vector in that subspace. So the iterative procedure is a little bit different conceptually this time than the procedures that we saw before. Okay, one thing that I just want to point out here, if X naught is equal to 0, R naught is equal to B. And if it gets to the point where there's too many subscripts for you, just imagine that R naught is equal to B, and that'll make things make a little more sense. I think things look a little more natural if you just tell yourself that R naught is equal to B. Okay, so what we're going to do at step M, at step M, we are going to form the space Km, which is going to be the span Km is going to be the span of the vectors R0, A, R0, all the way up to A to the power of M minus 1, R0. Okay, so notice there are M vectors. Okay, and we're going to look in the case where L, we're going to make a we're going to do a projection method where L is equal to Kn. Okay. So now what we're going to do at each step then, so now that we have formed this subspace here, at each step we're going to form a new vector. We're going to call it X sub M, and it is going to be equal to X0, okay? Not Xm minus 1, it's going to be equal to X0 plus delta, and we want B minus A xm to be orthogonal to Kn. We want B minus AXM to be orthogonal to Kn. Okay, so let's see. I kind of want to use this space here to do some work. So let's see. Let me just recopy this down over here, and you'll get to hear me say it again. So at step M, we form the subspace Km is equal to R0, AR0, all the way up to A to the M minus 1, R0, and it's actually the span of this, so Km is going to be equal to the linear span of this set. In other words, all of the linear combinations of these vectors, and Lm is going to be equal to Km. And so at each step, we're going to set Xm is going to be equal to X0 plus delta, where delta is in Km, and B minus AXM is orthogonal to Kn. Okay. Now, if we unpack what this step is here, this is going to be B minus AX0 minus A delta. Now, delta lies in the subspace Kn. So we're going to figure out a way that we can write delta. Well, it's going to be a matrix whose columns span Km times Yn. So okay, so this is what we have here, and I'm going to just write this as, for now, B minus AQ naught minus A, and I'm going to write Qm Ym. Qm is going to be a matrix. The reason I'm using Q will be apparent in just a moment. Qm is a matrix whose columns span the space Km, and then Ym is going to be an m-dimensional vector. And so as Ym runs through Rm, Qm times Yn will run through delta. This is very similar to things that we've seen so far. Okay, so that's going to be orthogonal to Km. Okay, so there is an approach to this problem that if you are comfortable, I don't know where my piece of chalk is. If you are comfortable with some linear algebra concepts and orthogonal projections and stuff like that, will make a lot of sense. But it's actually not going to be the method that we end up using. But it helps us understand the basic idea of what we want to do. Okay, so we're doing this as an iterative process. So by step M, we've already formed this space up to M minus 1. So it's at step M, we're going to form this new space. By step M, we have formed Km minus 1. Now, let's say we have an orthonormal basis for K M minus 1. So let's say I have so I'm going to give basically an inductive way for how we can form an orthonormal basis for Km. So let's say we have an orthonormal basis for Km minus 1, and let's say we're going to call this W1 up to W M minus 1. and this is an orthonormal basis for km minus 1. That is this set, but we're going to go up to a to the power of m minus 2 rather than m minus 1. And I just want to point out this isn't a typo. This should be m minus 1. So this is correct. I'm just erasing it because my 1 looked like it too. Okay, so there are m vectors here. Anyway. Okay, well then how can we come up with an orthonormal basis for Kn? Well, the most obvious idea is to just do straightforward the Gram-Schmidt process. Now this is not what we're going to do, but it's going to give us some formulas that are going to be similar to what we actually end up doing. So what I can do is I can form my new vector am minus 1 times r0, and I can basically Gram-Schmidt this onto these vectors here. And so my new vector is going to be equal to Wm, and actually I'm going to put a tilde over it for now. This will be the non-normalized version. Wm is going to be equal to a m minus 1 r naught. And now I'm going to subtract off the projection of this vector onto the previous vector. So we're going to look at k equals 1 to m minus 1 a m minus 1 r naught wk. And then Wm is just going to be Wm tilde normalized. So it's going to be Wm tilde divided by the norm of Wm. And now, I didn't have to create an entire orthonormal basis from scratch. I just took my next vector and did this, and now I have an orthonormal basis. So now I have an orthonormal basis for Kn. Okay, so what can I do with this? How can I actually make some computations with this? Well, recall that if W, let's see. So let me just say it this way. So I'm pausing a little bit because I'm using different letters than what I planned to use, and now okay. So if V is equal to the matrix whose first column is R0, whose second column is AR0, and whose final column is A m minus 1 R0. In other words, the columns of V span the subspace Km. Then this Gram-Schmidt orthogonalization process we just did gives us a factorization of V. V is equal to Q times R, where Q, the columns of Q, are just going to be given by these orthonormal vectors here. So W1 all the way up to Wm, and this is upper triangular. Okay, and now what we have now, again, Q is an orthogonal matrix, meaning its columns are mutually orthonormal to each other. R is an upper triangular matrix. So this Q is this Q. Maybe I'll even put it in here. And so the columns of Qm, they span the space Km. Okay, it's just the orthonormal basis for Km that the Gram-Schmidt process produced. Okay, so what this means, if we look down here, we want this vector here that I'm putting in parentheses. we want that vector to be perpendicular or orthogonal to Km. So what this means is we want Qm transpose times B minus AX naught, that's R naught. So we want Qm transpose minus R naught, Qm transpose times R naught times A Qm to be equal to 0. If we distribute the Qm transpose and move keep the Qm transpose over here and move everything else over there, we're going to get Qm transpose R naught is equal to, there's a Ym here that I did not put here. Okay, so we're going to get Qm transpose R naught is equal to Qm transpose A Qm Ym. Okay, so I'm going to erase this, but when we get down to this equation right here, Qm transpose R naught equals Qm transpose A Qm Y. Okay. Okay, so we have this orthonormal basis, and we're going to say Qm is the matrix whose first column is W1, all the way down the last column is Wm. Then what we just showed, what I just erased, is that Qm transpose A Qm Ym is equal to Qm transpose R naught, like this. Okay. So at each step then we need to figure out what Ym is. And so the idea is then we're going to solve this system of equations. Okay, we want to solve this system of equations for Ym, and then we're going to have our update xm is going to be equal to x naught plus Qm Ym. Okay, there are two problems. There are two problems with this. First of all, this is not necessarily an easier system to solve than what we had before. Second, in this Gram-Schmidt orthogonalization process, the problem is that as we're just computing, literally we're just computing bigger and bigger powers of A applied to this vector R. Okay, the problem is that A could have very big eigenvalues, or it doesn't even have to be very big eigenvalues. A could have eigenvalues that are bigger than 1. So what's going to happen in this case? So let's say that we want to compute A to the power of M times R naught. Now let's assume that we can diagonalize A. So in other words, there are, if we're dealing in n dimensions, A has n linearly independent eigenvectors. And so if this is the case, we can write this as the sum k equals 1 to n ck lambda k to the power of m times vk. Where here I'm assuming that the vk's are the eigenvectors of A and lambda k's are the eigenvalues. Remember, this is the standard formula here for if we can if we can diagonalize a matrix. In other words, if there are linearly independent eigenvectors. Now, if let's say the biggest eigenvalue, lambda n, is greater than 1, then lambda n to the power of m grows exponentially. Then lambda n to the power of m grows exponentially. So what's going to happen for very big values of m, or maybe not even very big values of m, this is going to be roughly equal to Cn times lambda n to the power of m times Vn. So in other words, each time we form the new vector to add to this space here, it's basically just going to be a multiple of this vector. It's basically just going to be a multiple of Vn. Now, if we could do precision arithmetic, that wouldn't be a problem. But in practically speaking, this is a problem because, again, after just a few iterations, all of the vectors are basically going to be, parallel to this vector Vn here. And so what this means is that as we bring in new vectors to Km, those new vectors that we're bringing in are just almost parallel to each other. Okay, so what we want to do instead, and we'll explain this in the next video, is we don't want to just keep applying A to R naught. Essentially, what we want to do is we want to apply A to sort of the part of a vector that is orthogonal to the first set of vectors. Okay, now I know that makes little sense without having explained it, but this is going to be the idea behind the Arnoldi algorithm. What we do is we assume in each step we have an orthonormal basis for the previous set of vectors, and we're going to now apply A to the last vector of that set. Now, that last vector of that set is orthogonal to all of the vectors that came before it, so we're not going to have this problem that we mentioned here. Okay, so that's it for this video. This gives a very basic overview of the methods that we're going to be applying here. But now in the next video, actually it's going to be several videos because there's some linear algebra stuff, or there's some formulas that need to have happen to make sure some of the formulas work out how we want them to. Anyways, what's going to happen is I'm going to show you the real way that we're going to implement this one method called the full orthogonalization method. That is not a primary method that gets used, but we're going to show how this leads to methods that do get used.